y'all, it's Mrs. Verona with another mini lesson on balanced equations. We're going to go ahead and start with these two, synthesis reactions and a single replacement reaction. When I look at this reaction, the easiest thing to do is to make a T-chart. And you're going to want to list your elements down. So I have nitrogen and oxygen, because nitrogen gas plus oxygen gas goes and produces dinitrogen pentaoxide. Okay, so I'm going to put my two elements on this side. I'm going to do exactly the same over here. It makes it visually easier if you align them. Okay, so I have two nitrogens on this side. I've got two oxygens on this side. I've got two nitrogens here, and I've got 5 there. So right now I'm not balanced. My nitrogens are good, but my oxygens are not. So I want to go and balance it out. Now, I can't go and make this 2 into a 5 without using a fraction, and we don't want to do that. So I'm going to go ahead and put a coefficient of a 2 and distribute that out. So 2 times 2 is 4. 2 times 5 is 10. So now I mess up my nitrogen. I'm no longer balanced, but it's okay because I can go to the reactant side and balance it out. So I got a 4 here and I got a 2 here. I'm going to go ahead and put a coefficient of a 2. Distribute it out, so that's 4. So now my nitrogens are fixed, 4 and 4, no big deal. Over here, I'm going to put a coefficient of 5. So when I distribute that out, I've got 10. So now that I look at that, I've got 4 nitrogens, perfect. I got 10 oxygens, I'm now balanced. So if I go to my equation, that's 4, that's 4, that's 10, that's 10, perfect, it's balanced. All right. So now let's look at my single replacement reaction. I'm going to go ahead and go in the same exact manner. I'm going to go ahead and put my T-chart here. I have potassium, boron, and oxygen. So potassium metal plus boron oxide reacts to produce potassium oxide plus boron. So I'm going to write them exactly the way I see them here. Okay, I want them to line up where it's easy to go and visually see them across. And this one's a prime example. I didn't have KBO, I had KOB. But once again, it's easier if I leave them in this fashion. So I have 1 potassium, I have 2 borons, and 3 oxygens. I come over here, I have 2 potassiums, 1 oxygen, 1 boron. So now I look, 1 potassium, 2 potassiums. But this is a single guy, so I always want to deal with him last because he's the easiest one to manipulate. Okay, but I also know I have a single guy over here, boron, another really easy guy to work with. So once again, I'll wait till the end. I have 2 borons here, 1 there. I got 3 oxygens here and 1 there. So let's go ahead and take care of the oxygens. If I have 3 on this side and I've got 1 on that side, I'm going to go ahead and put the coefficient of a 3. So when I put the 3, distribute, I now have 2 times 3 is 6. 3 times 1 is 3. So oxygen has now been fixed up. Well, now I have 2 here and 1 there. So I'm going to put the coefficient of a 2 on this one because he's a single guy, so he's really easy to manipulate. So now my oxygens are fixed, borons are fixed. Now I only need to fix my potassium. 6 on this side, 1 on that side, put the coefficient of 6, and there you go. 6, 6, 2, 2, 3, 3, I'm now balanced. Yay! Well, let's just double check on the equation. 6 potassiums, 3 times 2 is 6. Perfect. 2 borons, 3 oxygens, 3 oxygens. I am balanced. All right, so this is my single replacement reaction. If I want to break it down to the letters, and hopefully you saw that in the free APs. So this is kind of like this A, B, C. Well, in a single replacement reaction, A is going to go and basically kick out B and hook up with C. And so we see potassium, oxygen coming together. So this is AC and this is B. So it follows our pattern for a single replacement reaction. Alrighty guys, we're going to go ahead and continue balancing our equations. Now we're going to deal with a double displacement reaction. Now our single replacement reaction had the single guy go and kick off somebody else to go and hook up with their partner. This one is really scandalous. All right, so if I look at my letters, this is like A, B, this is C, D. So A and D are going to hook up together. And then B and C are going to get together. So when you look on this side, I'm expecting hydrogen and hydroxide to come together. Now it makes water. If you think about it, H and OH makes H2O. Okay, so I'm going to go and put A, D, and then over here I'm going to have C, B. So it's going to be following that double displacement reaction. Now, whenever I deal with this one and I see my polyatomic ions, you want to look at them as like little chunks in between. Like this guy, this guy, this guy, this guy, that guy, that guy. And I'm going to break this up into HOH just because it's easier to look at them. I'm going to put them in red just to highlight what I did. Okay, so you have this guy and this guy. And now it looks more like what I was telling you, like A and D getting together. So you have hydrogen, you have hydroxide. So it's visually makes sense now. So same thing, I'm going to do a T-chart here. And I'm going to break them down to its compounds. So I have hydrogen, phosphate, potassium, hydroxide. Make them match up and make them line up. It makes it very easy to go across visually and see what it is. So H, PO4, K, OH. So I look at hydrogen, and I had 3 hydrogens, so I'm going to put 3. Phosphate. Be very careful because this is where I see the biggest oopsies. They see a 4 and they're like, oh, I have 4 phosphates. You have 4 oxygens, but not 4 phosphates. So be very, very careful. I only have 1 phosphate group. Now, the way I would know if I would have more than one of my polyatomic ions, it would be in parentheses and I would see a number on the outside, kind of like this. That would indicate I have 3 phosphates, but I don't see that. So I only have 1. I come here, I see 1 phosphate, and I have 1 hydroxide. Jump to the other side, potassium. I got 1 potassium, 1 phosphate, 1 hydrogen, and 1 hydroxide. Be really, really careful. Don't go and be like, oh, I have 2 hydrogens. Because you're looking at 2 separate compounds. You're looking at hydrogen and hydroxide. And so I know we know him as water, but he has all these fancy little names. He could be hydrogen hydroxide. When I look at H2O, he could be dihydrogen monoxide, but he doesn't like all that fancy dancy stuff. He just likes to be straight out water. Ooh, I just realized there's an oopsies here. All right, so this should be K3PO4. So I should have 3 potassium. Put this in black so it sticks out a little bit more. So he does, his subscript right here is K3PO4. Sorry about that, guys. All right, so now I look at this. I have 3 hydrogens here and 1 there. So I'm going to go ahead and put a coefficient of 3. And I'm going to distribute 3 times 1 is 3. 3 times 1 here is 3. This is the hydrogen part. But I only have 1 potassium and I have 3 on this side. So I'm going to come over here. I'm going to put the coefficient of 3. Same thing, distribute. That gives me 3 potassiums and 3 hydroxides. I think we're good, right? Let's see. 3 hydrogens, 3 hydrogens. 1 phosphate, 1 phosphate. 3 potassiums, 3 potassiums, 3 hydroxides, 3 hydroxides. Good. We're done. All right. So when you look at this one, the catch is make sure you keep your polyatomic ions together. Don't separate them. It'll make your life so much more difficult by separating these guys. Combustion reactions, these guys can also be a little bit of a challenge. So I'm going to break it down to a T-chart. So I'm going to go ahead and write down my elements. Every time I see my combustion reaction, I always think, I see a hope. I know, a little scandalous too, right? Here we are having elements like exchange their dates and hook up. And over here, I'm seeing a hoe. All right, you see, C, ho, cute, right? All right, so same thing on this side. You want to see a hoe on both sides of the equation. So I have 3 carbons, 8 hydrogens, 2 oxygens. I come on this side, I have 1 carbon, 2 oxygens. I've got 2 hydrogens, and I've got another oxygen here. When it comes to your reactions here for combustions, me personally, I like to separate them and have a 2 + 1. It makes it so much easier to see it visually, because if you would just put a 3, I've noticed that if I put a 3 here, people say, oh, 3 times 3 is 9. And that's not the case, because 3 times 2 is 6, plus 1 is 7. So I always recommend that you separate them 2 + 1 so you don't have that. So I have 3 carbons here and I've got 1 carbon there. So I'm going to go ahead and put a coefficient of a 3 here. So when I distribute, I've got 3 carbons and I've got 6 oxygens, okay? So that's why I was saying be careful, right? Because I don't want you to go and say, oh, I have 9 oxygens, because that's not true. So that takes care of my carbons. I have 8 hydrogens and I've got 2 hydrogens here. I'm going to solve my oxygen last because he's a singleton. And that's what I was saying earlier. Okay, so if I've got 8 here and I got 2 here, what coefficient do I need to put there in order to balance out? If you said 4, good job, you're right. So I put a 4 here. And I distribute out 2 times 4 is 8. And then 4 times 1 is 4. Now I'm going to add them together. 6 plus 4 is 10. So I've got 3, 3, 8, 8. Perfect. Now I have 10. I've got 2. So now, what coefficient do I want to put in front of the oxygen gas in order to get my 10? Okay, hopefully your head's already thinking 5, but if you can't get there, what you could easily do is say 10 divided by 2 equals 5, and that tells you what is the coefficient in front of oxygen gas. So now I distribute, 5 times 2 is 10. Okay, so I look at it, 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens. I have 10 oxygens on this side. Well, I've got 6 here and 4. 6 plus 4 is 10, and now this one's balanced. Hopefully it answers all the questions you got for balancing equations. If you have any more, please do me a favor and send me a message through Schoology or Remind. Thank you. Bye, guys.